Welcome, everybody. So today's webinar is all about accelerating XGBoost with Python, and I have a really exciting guest to introduce here. And Mike, can you introduce yourself real quick?
Yeah, my name's Mike McCarty. I'm a Director of Software Engineering at Capital One. Also participate on the advisory board at Prefect, and try to work in the community as much as I possibly can.
Great. So it's going to be a really cool presentation today. We're going to have a mix of a lot of different things. So we'll start with a few slides just talking about the whole landscape of XGBoost in Python, how we can make things faster, what Saturn does, what Capital One does with it. And then we'll go into a demo that Mike has prepared of doing some kind of GPU accelerated XGBoost. And then we're going to pivot into a Q&A session where I have some pre-prepared questions for Mike, but everybody who has questions, feel free to kind of drop them into the chat. You should see a chat on the right side there. There's an event tab where you can click the chat. And if you have any questions throughout the whole thing, feel free to put them in there. I'll keep notes of them, and then we're going to kind of tackle all the questions at the end. So for now, I'll show some slides. Great. Okay, so this is kind of what we're talking about. Lots of logos, lots of different pieces involved in this presentation today. So Mike kind of already introduced himself, but just in case anybody who doesn't know who I am, my name's Aaron. I'm a senior data scientist at Saturn Cloud. And if you have any more follow-on questions for either of us, here's our emails, our Twitter handles. You can totally just send us a message, shoot a tweet or an email, and we'd be happy to chat about any of this stuff afterwards. And so, Mike, I wanted to ask you, you discussed a bit that you have done some previous work within like the PyData world and Anaconda. Could you talk a little bit more about some of your prior work, maybe before Capital One, and then I think we'll get more into the Capital One stuff next.
Yeah, I mean, it all started for me many years ago in radio astronomy. So I spent the first 7 years of my career working in that field, and then bounced around a couple different startups. After leaving the observatory, ended up eventually at Anaconda, where I worked on the platform, and then a number of open source related consulting projects. One of them you can go see is called EarthML, and then that's where I started using Dask quite a bit in those projects, and then made some contributions to Intake, which is a data cataloging project that's still being maintained today. So.
Awesome. Cool. Well, in the way of intros, I think we just want to spend a little bit more time just talking about who Saturn is, and then into Mike's work at Capital One, just to give you some more context into why we're even talking about this stuff. So if you're not familiar with Saturn Cloud specifically, we're a cloud-based platform that really aims to bring together all of the best tools for accelerating data science in Python. So we have a platform that people can come in and use, and then be able to spin up Dask clusters for parallelism really easily, and then also take their work onto GPU machines and do some acceleration with Rapids and XGBoost and other tools that we're kind of talk through a bit today. We also have some integrations with Prefect to kind of tie everything together. So the idea is that you don't have to worry too much about infrastructure setup and all those things. You can get really up to speed and running really quickly within the Saturn Cloud platform. And the demo you're going to see today is going to be within Saturn Cloud. And then, Mike, do you want to talk a bit more about what you do at Capital One with Dask and XGBoost?
Yeah, so Capital One, I work in a group called the Center for Machine Learning. We're a group of ML practitioners and data scientists that help out other lines of businesses within an enterprise take the most advantage that they can from the ML landscape and what's going on in the ecosystem and the industry. Through a lot of that work, I've been fortunate enough to be able to contribute to Dask, mostly focused on Dask ML and Dask XGBoost. We've also been doing some work with the NVIDIA Rapids team as well to scale data science on GPUs. And that led to a lot of the work that we're going to talk about today with scaling XGBoost. And so, yeah, here's an example. This is a slide from a GTC talk that I gave last year And then last spring, we did an update. But this is talking about an example pipeline that we may run in Capital One. It's been kind of generalized for illustrative purposes here, but you can imagine you have this pipeline that's going through your entire process. This particular pipeline is not necessarily a scikit-learn pipeline, but say it's a workflow pipeline. Maybe it's Airflow or Prefect or something like that. Kind of traditionally, we've had a lot of CSV reading and writing between these steps, and we're working to kind of slow to speed that up and allow for data communication direct on Dask clusters or Rapids clusters between each one of these steps. But the work that we did here that we're highlighting is focused in on the training step. What we wanted to do here was look at they were using XGBoost and basically just spinning up a large instance on AWS and waiting for training to complete. And then they would kind of manually divide their data to kind of manually chunk it and train different GPMs and things like that, and figure out how to merge them together. So what we wanted to do was see what we could do with Dask XGBoost, and then also configure XGBoost to train on the GPUs. This was shortly after the Rapids team had and other folks in the XGBoost open source community added GPU support to the library. So along the left, we have kind of where we started. It was about 40 gigabytes of data. It was actually downsampled. It was only 4% of the total data available. For this particular data set and this particular model with these type of parameters, we were able to get 100x improvement on the training time, which was really fantastic. And you can see a plot there on the right. It's a log scale on the y-axis, just to kind of so you can see the actual blue data point. That was the original training time. And then we did a scaling study where we slowly added more GPUs, but held the memory constant to kind of train or to determine what were the performance increases that we would get as we were adding more GPUs. And in Rapids Dask land, that's adding more computer workers to the cluster. Yeah, and then the other thing that was really cool that we realized was, if you are able to get on-demand instances on AWS and you can spin up your clusters quickly, and you're only paying for the compute of the training, we were able to get 97% cost reduction from the original blue dot there, because that instance is running, as you can imagine, for quite some time.
That's great, and I think there's some more cost details we've got here. 97% cost reduction is huge, and I think is a game changer, really, for all of this.
Yeah, and this is some more benchmarks that we ran. One of the funny thing that you see here is we went from 40 gigabyte to over 1 terabyte. So remember when I said that was only 4% of the original data set? The first thing that the data scientists want to do whenever we give them faster training is they want to train on all their data. So we figured we would benchmark that as well. We originally oversized the cluster to 12 nodes, what you can see there. It turns out we actually didn't need that large of a cluster for training due to spilling to system memory and things like that. So we resized the cluster to 2, and that's how we get that final number. So what was cool here is that when we trained on all of the data, we were able to perform the entire training on maybe, so it's 22 minutes there. The original training time was 2 to 3 hours. So I remember that's on 4% of the data. So with all the data, we could train faster.
That's intense. And I think it's really a paradigm shift when you start working, especially like on GPUs, and then you go to multi-node and cluster stuff, is that data scientists can typically just get used to and accustomed to downsampling, right? Because it used to be that we can't really, do, like, it just, things won't finish in time or data won't fit into memory. And so I think it's really cool to share some of this information, because that does kind of turn the light bulb on people's head and change their way of thinking of like, no, we should use all the data because our models are going to be more accurate, and we can now that we have accelerated tools to utilize on GPUs. Cool. And so this is like a really awesome case study, all about like how we, what GPUs do, when you use them with XGBoost, how much faster you can train your models and such. So, the next question inevitably is like, okay, well, how do I do this for myself? I'm not at Capital One. Can I also run all of these things, right? And so that's where we kind of want to just talk about this kind of ecosystem. XGBoost is a really tried and true kind of machine learning tool within the data science world, and there are a lot of tools that interact with it, a lot of kind of software packages that aim to accelerate it. So we want to give a little bit of kind of just background and some context, and then discuss why we're talking specifically about Dask and Rapids here. So this is aiming to kind of show you all of the different options when it comes to open source Python tools for accelerating XGBoost. So when you're thinking about just XGBoost and all the different ways you can access and run XGBoost, the list is a lot bigger than this. But we have this list specifically because our audience here are Python data scientists, and we want to focus on open source tools that actually will accelerate XGBoost. So the tool is one thing, right? But you kind of need other hardware when you go to scale, right? If you're gonna scale to a cluster, you need multiple machines. If you want to accelerate on a GPU, you need a GPU or multiple GPUs. So that's kind of the way that we're breaking it down here. So when you think about all the way here on the left is the single node situation, right? That's just you're importing XGBoost on your laptop or some big EC2 instance, and then you're running with it. So H2O here does have an open source library kind of built around XGBoost, where they extend some of XGBoost to accelerate it a bit. But then when you go to a multi-node situation is when you have a large amount of data, typically then you have to go over to this multi-node and kind of cluster distributed paradigm. And there are a few other solutions here when it comes to actually cluster computing with XGBoost. And I think it's more of a testament to how mature and widely used XGBoost is that there are libraries and all these different tools that different people are using, and that way it's accessible for them to use it. So Dask is one that has kind of a multi-node implementations of XGBoost, and we're going to talk a little bit later more about some of those details. There's other tools like Kubeflow, Ray, and Spark that also do have kind of cluster XGBoost support. I think Dask is probably one of the more mature ones. The other ones are relatively new, and Ray specifically is pretty new within just the last few weeks. When we go over to the GPU side, and that's you can add multiple nodes, you can add a cluster when you have large amounts of data, and you're now able to kind of train on more data than you would before. But if you want these kind of 100x super fast speedups, that's really when you have to shift over to utilizing GPUs. So the XGBoost native package has an interface and options for accelerating on a single GPU. So you just got to make sure that everything is hooked up with CUDA and whatnot on your machine. And then if you have a GPU, if you have an NVIDIA GPU, you can actually use XGBoost. And because of that, the H2O wrapper also does support that. But when we go over here to all the way at the right now the only options for multi-GPU or multi-node multi-GPU is using Dask and XGBoost. So when I say multi-GPU, I mean if you have a particular machine that has more than one GPU on the same machine. So there's machines on Amazon, those are the ones that Mike was showing that Capital One was using. They'll have 4 8 GPU cards with that single machine. Or if you have a home rig that has multiple GPUs, you can do that. And then when we say multi-node multi-GPU, that means multiple machines that each either have a single or multiple GPUs within that machine. And Dask comes in to orchestrate all of that communication between multiple GPUs or multiple nodes and multiple GPUs. And so that's why we're focusing specifically here on Dask and XGBoost, because it is very mature and it has the GPU support. So as far as software interfaces, I want to go through a few of the different ways that you might kind of do all of these different scenarios. So I'm going to fly through the code here. We'll post a link to the slides in the chat towards the end of the talk, so you can kind of grab this and look at it yourself. But these are just really meant to be examples and showing you what's going on here. So the first one is the multi-node CPU setup. So in this case, what you need is a Dask cluster. So there's a lot of different ways to launch a Dask cluster. In this scenario, I'm showing you the Dask Cloud provider package, which hooks directly up to your AWS account and can launch Dask clusters within AWS. All you got to do here is initialize the cluster. And so this is a Dask part right here where you initialize the cluster and the client. And then the next part is using the XGBoost.Dask module. So within the native XGBoost package, there is an integration with Dask. And then what you have to do is just you have to pass the client, your Dask client, however you created it. It could have been in Yarn, it could have been in HPC, it could have been your own home-rolled Kubernetes, anywhere that you have a Dask cluster. All you got to do is pass in that client, and then the XGBoost package knows that it's working with Dask, and it'll make sure to spread that across the cluster. So this is here, I'm showing you the functional API, the one on the right. It's the same setup, except it's the scikit-learn API where you can create an object of a Dask XGBoost classifier. And now when it comes to the single GPU, this is now if you're still on one machine using one GPU, this is straight out of the box with the native XGBoost package. There's a lot of setup that you might need to do to make sure that your GPU is hooked up, to make sure that it's actually communicating properly. That's kind of outside the scope of this. Here, I'm just showing you what your code would look like, really what you would need to change in your XGBoost code to actually utilize the GPU. And in this case, you have to pass in an argument to tree method called GPU hist. So if you're using the functional API, you pass it through the parameters dictionary. If you're using the functional API, you'll just pass it as a keyword argument. And then that tells XGBoost, okay, I'm going to be training my trees on the GPU instead of a CPU. We take that even further now, and we want to go to multi-GPU. And so this is where Dask comes into play again. So it looks really similar. It's really a combination of those first two that I showed you, right? So we're initializing a cluster right here. We're getting a client, and then we're using the XGBoost Dask module, but also passing through the GPU hist argument. And the same works with the kind of scikit-learn API. So, this is, again, a brief overview. Mike's going to actually show you a demo of it running live. And we just want to kind of talk about a couple of considerations because currently actually out there's a couple different implementations for using Dask and XGBoost together. So previously there was this package called Dask-XGBoost, which was part of kind of like the Dask ecosystem, and it was a package to bridge Dask and XGBoost together that you would kind of install this package separately, and then Dask and XGBoost would be able to communicate. Now, more recently, there's a submodule within XGBoost, which is the code examples that I showed you, which is now the recommended Dask API for XGBoost. So if you go to the GitHub page for the Dask-XGBoost package, it'll actually recommend to use the native XGBoost.Dask module. There are a couple considerations when you're using these tools. I think as time goes on, these are going to smooth out and kind of won't have to worry about these things. But if you're going to get on it right now and want to run your own kind of Dask and XGBoost together, these will help you so you don't hit some of these roadblocks. If you are using the Dask-XGBoost package, you actually need to pin your XGBoost version to 0.9 or below, because the newer versions of XGBoost become incompatible with the Dask-XGBoost package. And so really I would recommend that you use the XGBoost package, the native one, but there's one reason why you would not be able to use this native XGBoost.Dask package currently is if you're using Dask Kubernetes clusters. That's because there's something in the XGBoost package itself that there's some challenges with it there are some challenges working with Kubernetes in that case. So they are fixed, and they're coming out in the next release of XGBoost, which is probably going to happen really any day now, honestly. Should be this month. So again, if you're watching this in a few weeks, you can probably use the XGBoost.Dask package. As long as you're greater than version 1.3, you should be good to go. But if you are using Kubernetes, then you might need to drop back to this Dask-XGBoost package, but then you'll need to pin your XGBoost version. So that's why we want to talk about some of these tips and tricks, because these are things that we'll encounter kind of going through it, and we want to make sure that other people don't encounter that as well. But again, if you're watching this in a couple months, probably you're going to be fine using the XGBoost.Dask package. Also, when it comes to the Dask Cloud Provider package, there are some challenges with using getting AWS GPU machines there, and so you kind of have to consider that as well. Mike, I know you had another one you wanted to talk about here with this XGBoost threading limitations.
Yeah, the other thing on your previous slide, just another point to make is if you are going to use Dask XGBoost and you want GPU support, you're going to make sure that the underlying the version 9.9 of XGBoost that you get was compiled or built with GPU support. That can be tricky sometimes too.
Yeah, that's good to know. That's a good point.
Okay, I'll talk about the bug. Change the slide. Yeah, okay, so this is an issue. Hopefully you guys can see the code here. This is an example in the issue that we ran into with threading and calling predict on an XGBoost object. And the example of the code here is the minimum reproducible example that we came up with to demonstrate the issue. It turns out this is actually documented in the XGBoost docs. And I linked those docs there on the slides, so when this is available, you can go check that out. But this is interesting. Essentially, the problem here is if you have a trained booster and you're going to call predict on it in a multi-threaded environment, the docs state that you definitely want to make a copy of that object or load it after you fork the thread. And one of the issues that you can run into is scoring becomes unpredictable, let's say. And so this was a reproducible example that kind of detects that. We opened the issue, worked with those developers to come up with the in-place predict that they created, which gets around this issue. But it's something to watch out for. And yeah, those are some screenshots. If you go to the next thing there's screenshots of the docs that talk about this issue. So that's something to watch out for.
Great, cool. Okay, and so those are a couple of the things when we were talking about just some of the tips and tricks and kind of just like things that we've encountered. If you're jumping into this, you might want to kind of consider those. And so I mentioned a little bit about this when we're talking about some of the GPUs and also using like some of the Dask kind of cloud packages, is there can be challenges sometimes with infrastructure. And so this is the part where I'm really going to kind of talk about Saturn Cloud and then talk about how we kind of help with this whole world. And then we'll go into a demo. But the key here, what we offer with Saturn Cloud is you can see this project page that we have. So you can create a project within Saturn and kind of name it something and then associate some kind of image with it. I know that's kind of hard to read, but right now you can see that there's an image. There's an image here called Saturn Cloud, Saturn something. And so what we'll do at Saturn Cloud is we have Docker images that are already pre-built with a lot of these packages. So all of those considerations about pinning XGBoost or using Dask XGBoost or using XGBoost Dask, we have kind of done all that work, went through it, and then we have pre-built images that anybody can use to kind of run all this stuff. So at least that's one part that's abstracted away and you kind of don't really have to think about that much. If you want to create your own custom images, you can also do that. And that just is all that's involved there is kind of copying and pasting in a conda environment file or a list of packages that you would want installed. And then we handle all of the packaging up of the Docker image and then making sure that's available. The idea is that you don't really have to know what Docker is or how to use it. You can just kind of come into Saturn and start running. And so you have two main kind of resources when you're working with a project within Saturn. One is the Jupyter server, which is the single machine that you're running. That's where all your code lives. That's where your Jupyter lab lives. So you can pick a machine that has 4 cores up until 64 cores and 500 gigs of RAM. You can also pick machines that have GPUs. So 1 GPU, 4 GPUs, 8 GPUs. And that's kind of what we're going to go through in the demo. And then you can also attach a Dask cluster. So if you wanted more power than what you had on your single Jupyter server, you can then now scale up to a cluster of any number of nodes that you would want, all right here from within this interface. And then you'll see in the Jupyter lab how kind of all of this stuff interacts. And so, yeah, and under the hood, we're doing a lot of the Kubernetes infrastructure work for you. And so then, similar to the screenshots that I showed you before, I was showing you the kind of pure open source Dask cluster creation using the Dask Cloud Provider package. In this case, you just have to swap out a couple of lines of code to actually operate within a cluster inside of Saturn Cloud. So in this case now, I'm using the Dask Saturn package and importing a Saturn cluster, and then I can create it and say, this is the scheduler I want, this is the worker that I want, and this is how many of them that I want. And so you can specify some of those arguments within the UI that I just showed you before, or you can do it right here in your code. But then at the end of the day, you're getting this client object back, which now this is just a Dask client. Dask abstracts away like what the infrastructure is behind the scenes. And then XGBoost now knows to work with this client as if it was just any other Dask client. But the key that we provide here is kind of the ease of maintenance and infrastructure setup with Saturn Cloud. Here's a couple links to references, but before I'll come back to this reference slide, but I actually want to just pass it over to Mike now because he's got a demo actually running within Saturn Cloud of doing some multi-GPU XGBoost training.
Okay, so what I have here in Saturn Cloud, I'm running a Jupyter server. I'm not running a Dask cluster like what Aaron was talking about. This is just the Jupyter server. However, it's running a V100 instance 16XL. That's going to give me 8 GPUs and a bunch of cores and other things. And I'm going to run everything on the Jupyter server, but I'm still going to use Dask because I want to utilize all 8 of those GPUs for training. And I'm going to talk you through that. So this case is a single instance, but multiple GPUs. Okay, that's my dashboard. And let's go ahead and refresh that because I had turn that off. Okay, yeah, I'm not running it right now. So I'm just going to run through this notebook. This is an example. This is actually taken from the Saturn Cloud examples, and I've modified it to run with XGBoost on GPUs. So I'm going to create a local CUDA cluster. Just run this real quick, and that will give me pass that off to my Dask client. That will give me the dashboard. So if I refresh this now, this should come back up. All right, good. Excellent. And this is straight up from the examples. I'm going to download part of the NYC taxi data set, and then just going to print out how much data I have because I'm only sampling 30%, and then print out the memory usage. So now we're going to download some of the data. See the Dask cluster light up. Resize this so you can see everything that's going on. There we go. And then this next step is straight from the example as well. One of the things I wanted to point out here is, as we'll see down below, we're going to actually perform grid search on our scikit-learn XGBoost object, passing in this data. XGBoost has its own grid search, but you may want to use the scikit-learn API. And this example shows that you could take this pre-processing method and conform it to the scikit-learn API and run it alongside of your grid search if you wanted to. And so you'll see an example of what that would look like. And that's why you might want to use grid search with XGBoost, even though it has its own grid search built into it. So if you have a pre-processing step like we had there, you wanted to use the pipeline API or the scikit-learn API in some way, you could do that. All right, so now we're going to run the pre-processing. We're going to persist the data onto our Dask cluster, and then we'll get into the grid search step. And just walking you through that while that's running, it's just plain old scikit-learn grid search using XGBoost. This is version 1.2, simple param grid. And we're going to use the built-in XGBoost evaluation results. We're configuring that to be right here. We're configuring that to be RMSE. And then what we're going to do is we're using Dask XGBoost here, the native Dask integration. We're using a Dask regressor. We're going to configure it to with the GPU hist tree method. This is going to tell this particular XGBoost regressor, whenever it's running on the Dask cluster, to use the GPUs that are available. And since we're passing in the client that's connected to the local CUDA cluster, it's going to use that, and we're configuring it to use the GPUs for the training. And then we just pass that off to our parameter grid. And now we'll run that, and we'll get some warnings. But what we'll see here, and I'll make this a little bigger. What we'll now see is we're gonna do some stuff in Dask on the CPU, essentially the folding and the splitting for the CV. And then you'll see the XGBoost training take off. You'll see GPU work happen, and then we'll go back over and do some Dask work. Now this is going to complete pretty quickly, but there's an opportunity for improvement here that we're talking about within the Rapids community, and that involves how do we build some kind of grid search object that can communicate with the XGBoost training just through some coordination, and then we could keep all of the data hopefully on the GPU, and we don't have these kind of underutilized GPU cycles here. But it's still pretty good, and that's the demo.
Yeah, it's pretty awesome. It's so cool to just be able to see all of the different things lighting up, to see that Dask is kind of running here doing its own tasks, but then you can look at the widgets in the NV dashboard, which is the kind of GPU monitoring Jupyter Lab widget, and just see like the memory light up, the network, and things going back and forth, and you can see kind of like all the different pieces that are happening. But kind of you as the data scientist training a model, it's just a handful of lines of code. You're writing a grid search the same way that you normally write a grid search, but then there's like all this work that has happened and is happening like behind the scenes to make this like super, super fast.
And there's not a lot of code. And then this completes in under a minute. This was a smaller sample of the data, but we were performing grid search, so we're training multiple GBMs there. One of the things to watch out for, you may think that, now I want to expand my hyperparameter tuning and add more here. This, obviously becomes a combinatorial explosion. As you add more parameters to this grid, there are limitations actually in scikit-learn itself, and we've run into some of those challenges as well of just resolving a very large parameter grid. So that's something, maybe some future work to do in Dask ML, since it also has a grid search.
Yeah, and I think we can kind of start to kick off some of the discussion here. So if anybody has any questions about kind of everything that we talked about, or anything that's on the screen here, we can kind of leave it up. But I mean, this kind of just leads me to some more like natural questions about this. And it's like you mentioned here that there is, I think on your grid search, actually, you had n jobs set to 1 to kind of specifically just do like one model training at a time. I can imagine that like if you were to now want to try, so the reason that this runs super fast, right, is because it's on a GPU. So we're training one model at a time, but because the XGBoost training and fitting is actually happening across these 8 GPUs, it's super fast anyway because each iteration is fast. But like, what if we wanted to actually also train multiple XGBoost models in parallel? I can imagine there might be some like GPU saturation considerations, and kind of like, what are your thoughts about that?
Yeah, we're using the Dask cluster here, that client. Remember, I passed that into the XGBoost regressor object. So we're using it for the GBM training, which means we can't use it at the same time, at least for the parallel job execution. So you always have to think about that. And use the Dask cluster wisely. Here, again, we're using it so we can train on all 8 of the GPUs.
Gotcha. That makes sense. And then, you think this could extend to, because I know you're using a local CUDA cluster here, like this is one single machine that's pretty beefy that has 8 GPUs, but maybe I wanted to extend it to like 80 GPUs. I had like a really big data set or a lot of kind of models to train. What's kind of your thought process for them going from this all the way up to that multi-node kind of multi-GPU situation?
Yeah, that's interesting. So we're using on a single a single machine, we've got on this type of instance in AWS, for example, we've got a pretty high speed interconnect between all the GPUs. There's been a lot of excellent work done on the hardware to make that possible by the folks at NVIDIA. As soon as you go to multi-node, you're going to go across the network, and so hopefully the instances types that you're using and the network support that they have there versus just the underlying network that's connecting all these things together, you're going to start to run into some networking issues. You're going to be network bound essentially because all of your individual jobs are completing really fast because they're on the GPU, and then you've got to move a lot of data around the network. So you want that network to be as fast as possible.
Gotcha. Okay. Yeah, that makes sense because when you're on the single machine here, all the cards are co-located, so they're going to have really fast communication. But then when you do multiple machines, then you have to kind of think about that.
Mm-hmm. And you want to factor that into consideration when you're setting up the infrastructure. You want to, like on AWS, you want to enable EFA, and you want to make sure that you're running NVLink on your instance configurations. Yeah, all that kind of stuff. Make sure that your infrastructure is configured to take the most advantage possible of the cloud services that you have.
Yeah, definitely. And so, we here at Saturn Cloud have that kind of Saturn cluster, right, that handles the multiple machines. It'll also handle kind of these multi-node and multi-GPU situations, and we kind of make sure all of that networking stuff as much as kind of Amazon has, because they're built on top of AWS, as much as Amazon has, we can kind of abstract away a lot of that for users who are here kind of trying to do these things. Okay, that's great. So this is really cool. Again, if anybody has any questions specifically about the code, feel free to put a question in the chat, or if you just have any general questions about like XGBoost or how Capital One uses it or how Saturn Cloud works, we're kind of here just kind of for this open-ended more Q&A session, just kind of anything that you may have. Again, I have a few questions that I can keep asking if nobody else has some, but if you do, feel free to kind of just drop them in there. So Mike, I know that you, at the beginning of the talk, we were kind of talking a lot about like that 97% like cost improvement and the crazy speed ups that you could get when you were doing the stuff at Capital One. And it's really cool and it sounds really awesome like when you're at the end of it. But I'm curious to understand like what were the biggest challenges that you had like as an organization and as a data science team, or I guess the first question is, why did you need to accelerate? Like, what were your challenges there? And then what challenges did you actually have when you started to kind of put Dask and XGBoost and GPUs together?
Yeah, well, the need for it is, like I said in the beginning, just waiting on that training time to complete. You can stand up a large instance and just wait for a while. Sometimes these jobs can take multiple days to complete. And then you'll run into an issue and you'll have to tweak your code and then restart the job. So that's just a really long cycle time, right? Of like a development cycle time even. And so some of the motivation was was driven by shortening that cycle time so that, if we can find issues in the pipeline sooner and tweak them, we can get models into production faster, right? Which is kind of the end goal there. As far as the challenges at Capital One for standing up a lot of this is standing up the infrastructure. I mean, inside of an environment in Capital One, we're obviously behind a lot of firewalls. We have a whole set of security in place to kind of like wall off all the cloud environments from the outside world. There are a lot of governance practices. Trying to take something that was not developed within that environment and bring it into it, it's very challenging. Like, for example, we may not have the particular kind of channels that the Rapids library publishes all the Rapids packages to. We may not have those mirrored within our internal environments. We got to bring those in. A lot of the underlying drivers, that we've got to build on the AMIs. We can't just use NVIDIA optimized AMIs. we have to get all that brought in, and then make that as fast as possible, right? Because the last thing you want to do when you're adding nodes to a cluster is run a lengthy user data script that's going to install a lot of packages, maybe even compile some binaries, all that kind of stuff. You want that to be fast as possible, right? So bringing all of this in and then also making it scale, making it as fast as possible within our highly secured environments was just super, super challenging. So.
Yeah, it sounds like the infrastructure pieces are where a lot of the challenge lies, right?
Yep.
Yeah. The software interfaces themselves are really good, really great, kind of succinct, straightforward to use. Looks like we have some questions kind of pouring in here. Related to actually the question that I asked, this is more about like, why were you actually using XGBoost at Capital One? What kind of tasks, if you're able to talk about them, were really the problems that you're able to solve there?
Yeah, I mean, without getting too much of the details, you can kind of get a sense for it. Essentially, decision trees and GVMs, can be really, really powerful. They can handle a wide variety of data. Of course, it's true with XGBoost. It doesn't handle categoricals, so you do have to preprocess your data a little bit. But they can be very powerful, but also they're explainable, right? And that's, for a regulated industry, that's something that's really, really important, is that the models that we are building, we can, from like a pure mathematical sense, be able to explain them and understand them. And that's something that you can do with GVMs, and they're very powerful and very flexible, making them a really great choice for our use cases.
Awesome. Yeah, it sounds like all the pieces kind of come together, and like that's probably why also so many others in the community find XGBoost so appealing and use it a lot. So that is that. I think you actually did answer another one of the questions that was talking about more about explanations and how you can kind of address that when using complex models. So that's great. So going through some more of the questions here, we are recording the event, so we'll have a recording up at the Saturn Cloud events page. So if you just go to saturncloud.io, you should see that within the next day or two if you want to go back through it. And I've linked the slides as well into the chat here, and we'll have the slides available for you there also. One question actually is based on what's showing on the screen. Charles had a question about what are the GPU monitoring tabs from within your Jupyter lab there?
These monitoring tabs, the GPU resources and the utilization. So yeah, this is a Jupyter extension that was developed as part of the Rapids project. I think I have a reference to it here.
I can throw a link into the chat.
Yeah, I can pull it up here too if you want to put it in the chat.
Yeah, I'll put the link.
So yeah, this is called NV Dashboard. It was developed as part of the Rapids project, and it's a Jupyter plugin that you can install. It gives you this little video card icon here, and there are a number of widgets that you can bring up to see what is going on the GPU and then on the network, and then also on the bus and on the machine, as well as you're running your model. And it's really nice. I use it to, with what you see here, to understand what's going on at different parts of the analysis, the preprocessing, and the training. So what was great about this example is that you could see the parts where XGBoost was training, and then the parts where Dask was being used to do some of the splitting and the folding of the data. And then you see some idle when you're moving data onto the GPU, and then you see training happen. So it's like very, very helpful to see what's going on. Sometimes nothing will happen because there's some error in your code and you're trying to figure out what's going on and where it's at. Is it in Dask or is it in Rapids on the GPU? It's really, really helpful to see stuff like that. Or is it just in scikit-learn? So for example, with the hyperparameter grid, if that's really, really large, none of these dashboards will light up at all. And you'll wonder what's going on. And you look at your Jupyter kernel and it's like at 120%. And that's because, something's going on in scikit-learn. And so helps you kind of figure out where the problems are, and when you're utilizing the hardware, help you tune to make sure that you're utilizing the hardware as best as possible, that sort of thing.
Yeah,
super useful.
As data people, it's all about the data, right? So it's like if you can watch and see and try to eke out every single kind of of resources that are available there. And so that is a Jupyter Lab extension that you actually can get installed. And so there's just a couple commands that you run that we ran here on the Saturn project. We'll probably in the future have it so it's kind of like automatically enabled for GPUs. And then when you go to kind of run on a cluster, when you're using multiple instances, the Dask dashboard actually has a couple of pages there for you to monitor the GPU memory and GPU utilization. So I think Dean in the chat actually linked to our hosted product. There's a free trial that you can try Saturn, and we have a couple of these examples kind of pre-built for you. There's one example, not XGBoost, but it's with like a Dask distributed like random forest across GPUs. And that example actually has showing you how you can launch a cluster with multiple GPUs and then how you can monitor it. And we have some links and some stuff in there. So when it comes to example notebooks, this specific notebook that we have on the screen here is not in that kind of pre-packaged stuff yet, but we are going to make sure that we'll get a tutorial specifically covering this and then some notebooks out on our GitHub and our documentation page. So definitely we're going to make sure that you have all the resources that you would need to kind of get going with this stuff.
Yeah, and right after this, I'm going to PR this notebook in the example repo, so people can get access to it if they want to run it on their own.
Awesome, that's great. That's great. Okay, so let's see. Okay, again, so there was actually one question back into the more of the XGBoost and use cases at Capital One. And as far as the explainability, are you mostly using SHAP? I know that's kind of a big common one. I've used that a lot myself. Do you use other things like Lime or maybe other tools?
Yeah, SHAP is really, really useful. There are a lot of great metrics just within scikit-learn as well that you can use. Another thing we'll commonly do is in XGBoost using GraphViz, you can actually visualize the tree. That's really useful as well. But certainly Shapley values are really useful from just from like a metric standpoint.
Gotcha. And something that I have and something that I ran into kind of doing my own research, working with XGBoost, Dask, and kind of this whole world, there's a lot of choices and a lot of options when you're going and looking, especially when you just search like XGBoost and you find that there's all these kinds of implementations. And Dask, there's a lot of things that work in this kind of Dask world. Do you have any kind of recommendations or tips for like navigating this whole sea of packages and implementations, or if anything, kind of what do you do yourself when you're seeing new things come out and trying to just make sense of all of it?
Yeah, so it's just thinking of all the different permutations possible, and then when you go, so like for example, your previous slide, when you're talking about the different ways, whether it's distributed Dask or one system, multi-threaded Dask, or one GPU, multi-GPUs, multi-node, multi-GPU. So trying to figure out like what's your topology there, and then that will kind of help guide which versions of the libraries you need to use. So like it can be challenging. So like for example, the Kubernetes issue that you mentioned, that kind of forces you to not use the latest version of XGBoost with Dask integration. It's getting a lot better though. Version 1.3, next version we're really excited about, and we'll probably, the Dask maintainers, have been kind enough to continue maintaining Dask XGBoost until this was ready. So at some point that will be sunset, I'm sure. And so the choices will kind of like narrow in eventually. But it's been a lot of trial and error, just starting with that topology. What do you want to do? And then figuring out what works, and just experimenting, looking at these dashboards, trying to figure out what's going on and where and when, and that kind of stuff. So yeah, it's been a lot of experimentation.
and it's great. It's like we're doing events like this and watching talks like this where people are talking about it who have done it before. Like I would love to just kind of, if I was new to this, come in, see something like this and be like, oh, okay, I need to use XGBoost.Dask, or I need to use Dask, or look at this. And so again, it's staying curious, looking around, understanding that this is like open source work that a lot of people in communities are all kind of working on together. We're in data science anyway, things move quickly, it's how it is, but we're all progressing forward and kind of moving forward. Speaking of which, actually, I did have a question about, I in one of the slides I was recommending to kind of when you're the Dask 1.3 package is now going to allow you to use Dask. Or I'm sorry, the XGBoost 1.3 version is going to allow you to use Kubernetes with kind of multi-node XGBoost. But what happens then when I imagine that you, as working through this, have gone through several versions and several releases of XGBoost. So what happens when you've got like a trained model on, say, like 1.1, but then 1.2 comes around? Do you jump on it immediately? Do you retrain your models? Kind of how do you think about new versions?
Yeah. So yeah, the answer there is no, you don't jump on them right away. Mostly because, once we are building a model and we're, targeting getting it into production, there's a whole process that model has to go through in order to make it there. And once we get a model that's working, it's from a predictability standpoint, explainability standpoint, it's performing the way we need it to. We don't want to change it unless like there's some issue with the performance of the model, right? So so you don't just jump to the new version whenever it's available. You have to kind of like walk this line between working around some of the issues with the version that you're on for your current build, and then keeping an eye on those new advancements and thinking about those for the next one. But that's something that you need to take into consideration and plan for. Yeah.
Yeah, that makes sense. Definitely, we did.
But you definitely want to pay attention to what's going on and participate in the community as much as possible, because that really helps.
Absolutely, and then each version, new things are happening. Things are getting fixed. It's getting more stable, so on and so forth. There was another question that just came in about your kind of cost slide when talking about scaling. I can actually bring this back up. Give me 1 second, just so we have some context for this. Back up. There was a question here about the fact that the costs were shown, and I think I even alluded to the fact that you can use more data and get better accuracy. Do you have a sense of like what the kind of accuracy improvements were when going from this like 40 gig to the 1 terabyte data set? Yeah,
that's a really good question. When we first did this work, we actually didn't know the answer to that question. Like, just because I can train on all my data, will that give me a better model? And so because this is a new capability, that's something that you'll need to explore. Once you enable that capability, you'll have to look at that through your model evaluation process, right? As you're building a model, you'll want to look at what happens when I add more data, what happens to the scores and the evaluation. Since then, we're finding that using more data is helpful. I mean, there's a point. You don't want to overfit, obviously. But when you're dealing with such large data sets, a little bit more data goes a long way.
Yeah, and I think it also really is very dependent. Just like most answers to questions in data sciences, it depends. It depends on your data. It depends kind of what you're predicting. And I think that's really true, and especially when it comes to the question of when I add more data, how much more accuracy do I get? There's really not a good way to just apply a rule or a function to that. It really needs to be kind of experimentally determined. So you can do a lift curve or a learning curve, excuse me. You can plot a learning curve, right? You just add a little bit more data. Even if you were at the 40 gig data set, you could go from 5, 10, 15, 20, kind of see how your accuracy increases as you add more data. And then again, you can see if you encounter any of those plateaus, because eventually it will kind of plateau or overfit, like you said. And again, it's just kind of experimental. And then, if you see that constantly getting more data gets more accuracy, that's when you can really take advantage of a lot of these accelerated exercises. And you can actually do that experiment a lot faster if you're accelerating things, because otherwise you'd have to wait for a long time.
Yep, that's right. Yeah, I think the takeaway is that you have the tools to answer those questions, and with the scaling that we're able to provide here, you can continue exploring that. So you're already it's the same thing that you're already doing in assessing the model performance as you're building it anyways. You just now have more data you can use.
Definitely, definitely. Cool. Well, we're actually just about at time. I have one final question to end it, and then we can kind of wrap up. What are you most excited about the future of XGBoost or the future of Dask and GPUs, all the stuff that we're talking about?
Yeah, it's definitely multi-node, multi-GPU training and overcoming some of the networking issues that we see. That gets me really, really excited because it's going to allow us to really push the limits here of what we're able to do with the stack. And then also, what's interesting is like when you're pushing on those edges of performance, of computational performance with these stacks, you're finding a lot of issues and then bringing those issues back into the core library, issuing fixes upstream and opening issues, or issuing PRs and opening issues upstream. Even if you're just opening issues, it's really, really useful for these developers to hear how their tools are being used and where they're needing some more attention. So it's really, really great to do. Yeah, super excited.
Great. Well, thanks again a lot, Mike. Thank you for joining in even so close to the holidays. Happy holidays to everybody. I forgot to mention that at the beginning. We got our little festive setups, and if you've noticed my big data Christmas sweater here. But again, thanks all for watching. If you want to get more involved and kind of see more about the stuff, you just got to go to saturncloud.io here. You can click the Start for Free button. You'll get a free trial within our hosted platform. You don't need an AWS account or anything. You just kind of put in your name and email. You get an account, you can spin up some machines, spin up some GPUs, and kind of get going. And there's also a couple of ways if you want to get more involved too. You can check out some of our events, and you can even kind of scroll down here and join our Slack community, because we have a Slack channel where we kind of just talk about some of these stuff, and we can talk about our Dask problems, talk about our GPU problems, or any kind of anything that might be happening. But again, thank you all for watching, and stay tuned for our next event. Thanks again, Mike.
Thanks.